Okay, good afternoon everyone. Thank you for joining. My name is Gan Chin Kim and I'm the Executive Committee of IEEE PES Malaysia for technical activities. Okay, welcome to IEEE PES Distinguished Lecturer Program. We are truly honored to have with us Dr. Nilesh Modi, who will be sharing with us his presentation on power system modeling for assessing impact of high penetration of inverter-based resources on power system security. Dr. Nilesh Modi is the manager of Future System Studies team at the Australian Energy Market Operator, AEMO, and an adjunct senior researcher fellow at the University of Queensland, Australia. With 17 years of experience in academia, research, and industry, Dr. Nilesh currently focuses on operating power system with a high share of inverter-based resources. So before we begin, just a few housekeeping notes. We'll have Q&A sessions at the end of the presentation. And please note that this presentation is being live streamed and being recorded. And with that, it's my pleasure to hand the floor over to Dr. Nilesh Modi. Over to you.
All right. Thank you, Gan. Can you guys hear me? Or is it okay? Not really? Okay. Struggling with this. It seems working okay. Now it's okay? All right. Okay. Thanks, Dr. Gan, for introduction, and thank you, Malaysia chapter, for inviting. Before I start, just a bit of a disclaimer that I represent IEEE PES during this talk. So the views presented during this discussion they are my own, not necessarily of my organization. Although I work for Australian Energy Market Operator, but what I'm sharing is as a distinguished lecturer for IEEE PES. How many of you are PES member? Okay, almost quite a few. Okay, that's good. So that helps me to go through this first section of the slide where I'll talk about IEEE PES. So PES sits under the umbrella of IEEE. Okay, so I'll quickly go through these slides because quite a few members are PES. They know the benefit of IEEE, and PES sits under its member-driven organization. Okay, under Technical Activities Board, you can see in here. There are 39 societies, 7 councils, and over 20 technical committees. And IEEE PES is one of the technical society. In fact, it is the second largest society in IEEE. Right? So if you are not a member, think about becoming a member of IEEE PES. What PES do? There are basically 4 categories of the activities PES do: technical community, conference and meetings, publication and educations. We have a lot of publications in terms of technical community. Plus there are 20 satellite communities. So if you are not really based in US, Canada, you can participate in IEEE PES activities through these satellite technical committees. As you can see on the screen, there are a number of PES standards and IEEE standards where PES participates. There is a list of recently published technical reports. You can go through them on the website. It's available there. A little bit closer. Is it better? I hope I'm not going to eat it. Okay. All right. That's good. Okay. In terms of conferences, so some of these logos might seem familiar to you, right? IEEE ISGT Asia. That's the Asia Focus Conference. PES General Meeting, one of the flagship conference in normally hosted in United States. We have the PES International Meeting happening next year in Asia Pacific region in Hong Kong. TND, Grid Edge, EPIC. So these are some of the flagship conferences. NGTD Asia, of course, it happens every, I think, 3 years. This year it is again going to happen in Thailand. In terms of publication, these are some of the really good publications. These are well-read, well-cited publications. It's specifically written, particularly PES magazine is particularly written for keeping in mind that not all readers are electrical engineers. So you will see lot of good information coming out from Power Energy Society PE magazine. Right? There are transactions, there are open access journal. Most of the conference publications would be available on the IEEE Explore. And there are 2 award-winning magazines, like I mentioned, Power Energy Society. There is a publication in Spanish as well. So if you know Spanish, you got option to read in Spanish as well. In terms of education, there are a lot of activities IEEE PES do. You've got a PES University. One of the best kept secret is PES Resource Center. If you go to PES Resource Center, you'll find a lot of information. You'll find a lot of recordings, a lot of tutorials, webinars. Everything is there, so you don't need to attend it in person. Even some of the panel sessions in the conference, they are getting recorded and put it on PES Resource Center. So I encourage you to go and have a look at PES Resource Center, and it's free for PES members. Bit of a global engagement. So there are 280 chapters all across the globe. Right, we are in region 10, Asia Pacific, and there are some numbers for the student, professional members, and student chapters. Right. This is normally a journey for PES member. Okay, I know I'm conscious that I'm going through slides really quickly, but you will have a copy of it, so you can read through each and every line at your leisure. But normally you have a student member, then become professional members. Professional members have a category like member, senior member, fellows, senior life, and fellows. And the why people join, that there was a survey, and then we asked people why they want to join. One thing came out common was the networking. You can see it's student member also mentioned networking, same as professional member, same as life member. So this is the really good stage where you can build your network, right? It will help you to build your professional career, whether you go down to become a lecturer in the university, or go down work in the utility, or start your own consulting firm, or maybe you pick on a startup, right, and build something new for yourself and for the community. Then networking is one of the things which IEEE PES can help you. With that short introduction, we'll start talking about power system modeling for assessing impacts of high penetration of IBR resources, and how do we assess power system security. We assess power system security through power system models, right? Most of you have started using power system model in your day-to-day life. And I always start my quote with this famous words from George Fox. Essentially all models are wrong, but some are useful. Right? So often modeling is not that easy. Garbage in, garbage out can happen. Right? In this talk, I'm planning to go through some of the background on power system models and these challenges. What are the types of model which we normally use? A bit of a difference about phasor domain models and electromagnetic transient model. That's what we discuss a little bit in detail. I'll quickly skim through the approaches for developing wide area EMT models, the wide area electromagnetic transient model. Bit about model validation, and I'll try and summarize the presentation in next 45, 50 minutes, right? I forgot my timer. Okay, it's okay. You just remind me, okay? All right. So if we look at the models, right? So what we mean by a good model, not necessarily accurate model, but you would be working with modeling in your study time frame, or maybe where you're working in your career. You look at the models. The good model should be adequate for various power system studies, right? So it should be able to help you with interconnection studies. So if you are a utility engineer and you are getting a connection application that, okay, I have a solar farm, I want to connect to your grid. So that model should be capable enough to run your study for the interconnection process. Coming back to system operations side, so if you are working in one of the utilities, right, and then you get asked, okay, can you assess the system performance? Can you assess the system security and develop a technical operating envelope? Those models should be adequate to develop technical envelope, so that system operator can work within that technical envelope and run the system, keep the lights on. Same thing for operation planning and forward-looking scenarios. Model should also be robust for the defined test conditions and the modeling domain platform. What do you mean by robust model, right? So when you get a model, you want to run some stories, right? It shouldn't crash unnecessary, right? It shouldn't throw you a lot of errors when you are doing it. That's not a good model. We are talking about the model usage, not the accuracy of model. The accuracy of the model will come later, right? So when you get a model, it should function well, right? You change the operating condition, right? Okay, now I want to test this plant at a 50% of its operating condition. It shouldn't crash for 50% operating condition, right? It should work as expected. It should provide as intended response. So these are some of the features you should look for in terms of system modeling. When I say intended response, that it should work in a design parameter. Okay, so you apply a minor disturbance when you are running some studies, and the model just crashes. It's not at intended response, right? If the model trips for a fault which is far, far, far away from the grid, well, it's unlikely to happen, right? So your model is not fit for purpose. It's not its intended response. So it should give you as desired response within the operating parameters. It should be with, consistent with the technology type. What I mean here, if you got a model of a synchronous generator or a synchronous machine, you apply a disturbance and it normally it is going to oscillate, right? And then eventually it will settle down. If you get a synchronous machine model and if you allow disturbance and there is no damping in the output, maybe it's a question, because okay, it's not a characteristic of a synchronous machine, right? You normally have those kind of a damping coming out from the model. So it should give you the consistent response with reference to the technology type. If you get a wind farm model, or let's take an example of a solar farm model. You get a solar farm model given to you, you apply a disturbance, and it all of a sudden start giving you this kind of a damping response. I say, okay, well, that doesn't make sense, because solar farm doesn't have rotating machinery, so it should not give you this kind of electromechanical type of response. Or you apply disturbance at the solar farm terminal and you see the voltage, sorry, not the voltage, but the fault current is like 3 to 4 per unit. And you say, okay, well, that's not really, you can't get that from solar farm unless you are really over designing it, right? So these are some of the checks and balances that are important to examine when you get the model. Just check, is it a good model, is it a robust model or not? And then you can start looking at the studies. When we do these studies, what we are looking for, right? What's the objective? What do you want to achieve? There is an error in this slide. It's not 2014, it's 2004. I figured out late. But I believe you should have seen this picture, right? Classification of power system stability phenomena. The right side of the box, which was proposed in 2004, which talks about classical stabilities, right? Rotor angle stability, voltage stability, and frequency stability. So it talks about all the transient stability, voltage collapse, right? Dynamic voltage collapse, etc., etc., right? So this is well understood by industry. In 2020, IEEE Power Energy Society Task Force extended this stability classification and added this portion which is called converter driven stability and resonance stability. Particularly, there is a growing focus on the converter driven stability, which essentially is the fast interaction of those inverter based resources plant, IBR. Those interactions are largely within the inner control loop and normally in the hundreds of hertz to kilohertz, and there are slow interaction which are normally associated with the outer control loop PLL and often associated with weak grid stabilities. Right? So you might have studied this part of the stability phenomena, but this is what is emerging nowadays. Right? So if you haven't had a chance to look at this this box, it's time to learn a bit more on this converter driven stability phenomena. So what's the impact? Okay, so people often talk about, okay, we are seeing a lot of renewable energy coming into the grid, a lot of IBRs coming into the grid. Is it going to be issue? What impact it can do to the power system security? Okay, so this is the one slide. Well, it can create harmonic resonances and subsynchronous interactions. Many system operators, I think I have a slide where I'll show you the examples. A lot of system operators have started to see this subsynchronous interaction, which essentially falls under the converter-driven stability as well. What they are seeing is they are seeing an interaction between a plant and a network. So if you got one of the wind farm or example, right, one of the solar farm coming to the grid, it's start interacting with the grid. So they're seeing, okay, it's only one wind farm, but it's interacting with the grid, and this is kind of a falling under the converter-driven oscillation or converter-driven stability. It may happen that you have multiple IBRs connected in the close proximity to each other, and they start interacting with each other. So network is like a bit of a conduit between them. Not necessarily network is reacting to it, but inverter 1 or IBR 1 and IBR 2, they are interacting with each other. So this kind of phenomena has started to appear in the grid, right? So this is one of the emerging stability phenomena. One of the example is on the top right figure, right? So you can see this is interaction started to appear here and kind of cease down. There is a bit of a discussion happening about interaction between power quality and system security. This is mostly, if you are working with a system operator or distribution system operator or transmission system operator, this would come to you that you see this kind of phenomena on the grid. So when you are operating the system or when you're looking at real-time data, you will see this kind of blips coming up here and there, and then say, okay, wait, yeah, so what? Lights are still on, right? Is it a system security issue, or maybe it's a power quality issue, because you really don't want this kind of signature on the voltage. You want voltage to be smooth and stable. So there is a fine line nowadays between power quality and system stability. Okay. On the bottom right, it's kind of a summarizing what could happen. So if you got a IBR and it can interact with another IBR, so it could be a wind farm, solar farm, or it could be a HVDC system, and it could create a control interaction, right? If there are IBRs interacting with let's call it rotating machinery, then it could create a subsynchronous torsion oscillation, right? So you might have this kind of a frequency of oscillation in the grid, which could coincide with the natural resonance of rotating machinery, and it could have a subsynchronous torsion interaction. And I hope you know that rotating the subsynchronous torsional interaction, right? When the shaft has number of masses, then it kind of interact and try and break it. Not try and break it, but it can damage the shaft. So what are the oscillation events? Whether is it a real? Have people seen it? Have system operator have seen it? This slide and the reference summarizes what system operators have been seeing in terms of IBR interaction. The one top left is the Texas event, which happened around 2008 in the Panhandle area in the airport, where they have a large concentration of wind farm in a let's say close proximity to each other, and they started reacting to it, and then they see this control interaction, and that's where this topic picked up. That was probably one of the earliest example of a notable incident in real world. And you can see many system operators across the world have seen this interaction. There are a couple of examples from Australia, you can see it here. Example from China, example from Hawaii. There is one from Scotland, Great Britain grid saw this kind of interaction. Germany, Canada, one more from China. So you can see this kind of incident happens in the grid, where the grid have a lot of inverter based resources, right? These are a little bit different than classical transient stability or voltage stability. You see it, right? It's not, system is not collapsing here, but it's interacting with each other. The plants are interacting with each other. Is it an issue? Well, yeah, it's happened, right? Plant interacts with one another. So is it really an issue, or should we just look at it and then ignore it? There are some incident I have listed on the slide where it demonstrates the impact of inverter-based resources on the grid. Right? There was a Odisha event in US 2022 where approximately 1.7 gigawatt of IBR unexpectedly reduced power. Okay, and they are IBRs, right? Is the 1.2 megawatt of fault-induced solar PV reduction report in 2016. This one from UK, where they have seen this kind of interaction, and I think that resulted into disruption in the system. A report from India where they have observed 31 events involving more than 1 gigawatt of generation loss within a year and a bit. So this is reality, right? Often people say these are oscillations, it can happen in the grid. Is there an issue? But there are incidents where it has resulted into disconnection of generation. If it is a small one, then it's okay. System can cope up. If it is large one, then it could have a catastrophic impact. Okay, switching a gear a bit. This was a bit of a background, impact of IBR on power system security. How do we assess it? Of course, we are engineers, right? We like models. We assess it to power system modeling. I've tried to summarize types of power system model. Again, these are not exhaustive category. That's why I mentioned there are non-exhaustive category of power system model. It's difficult to categorize every single model. But basically, there are three types of a model. A phasor domain model, or often people call it RMS model. Some literature you will see phasor domain transient model. Okay, so that's one category which are normally people use it for voltage transient stability, contingency analysis, frequency stability, and power flow. I'm pretty sure you would have used this kind of a RMS modeling, right, in your either in your study or maybe in your day-to-day work life. The second category here in the middle is the electromagnetic transient model, right? So quite a few system operators are now using electromagnetic transient model for assessing system strength assessment. So looking at the interaction between the IBR and the grid, or between IBR and IBR, right? That forms under the part of converter-driven stability. These are some of the models which can be used for system restart. So if system goes black, then you need to start the system. And how do you start the system? You first have some model, right? And then you look at the model. Okay, I want to start this generator, pick up this generator transformer, pick up this line, and then I'll pick up this load. And then I will go and in this direction and start picking up on rest of the load. So you can use electromagnetic transient model for system restart. And of course, these models are not really new, right? Those who have been working in the lightning and switching surges and insulation coordination, right? They would know that EMT models, they have been using it for some time, right? They use it for all the switching studies, transient studies. Right? But now it's extension of those EMT model into inverter-based resources interaction, or looking at impact of IBR on the system security. And the third category I have listed is the small signal model. So largely they are used for inter-area oscillation, electromechanical oscillations, right? Less than 2 Hz, largely. And these are essentially linear models, right? So basically it's assumed this system is in a linear state, and it applies the small perturbation to the system and look at how the system is going to behave for their small perturbation. What do we this model for? Okay, so one on the left hand side is basically, I would probably say, covers most of the power system studies an engineer is going to do in his life. Starting from the left hand side, in a microsecond time frame, right? So if we are interested in lightning propagation, switching surges, these are the studies where you do it in a microsecond time frame, right? You don't do that study for like 10 seconds. You just want to look at like few cycles and then do your study, right? If you have a lot of IBRs into the grid, then your time frame is somewhere in this line where you want to look at the interaction of the IBR, right? So those are not really fast transient time scale assessment. These are more in terms of millisecond assessment, right? So your assessment time frame is really small, so the time constant, right? And then one in the middle are more of a stator transient, subsynchronous resonance, transient stability. So in your career, you might be doing some transient stability analysis, right? Dynamic voltage collapse analysis. You're probably interested in this time scale. And if you are interested in the frequency control and primary, secondary, and tertiary frequency control, then you would be falling in this category. And boiler dynamics are pretty slow dynamics if you're interested in looking at the studies. So if I were to categorize this time frame, then these are the wave phenomena. These are electromagnetic phenomena, which I was mentioning it. Then electromechanical phenomena and thermodynamics phenomena, right? Basically, this covers the time scale a power system engineer would be interested in study. But how do we do that? There are two categories of model I have, EMT model and RMS models. Okay. And what I am showing you here is the bandwidth or the capability of those specific two types of model. So if you got RMS model, like most of you would be using it, right? Either through PSSE or there are other tools which runs the RMS power flow. Okay. It can capture this bandwidth of phenomena. So if you have a let's call it a electromechanical oscillation around 1 Hertz, right? RMS models can capture it because it has its capability. Its bandwidth is somewhere around up to, I would probably say, 8 to 10 Hertz, right? But if you have a lot of IBR in the grid, which has a lot of high frequency switching devices, right? Inverter based SOCs are basically high frequency switching devices, right? IGBTs, which often has the PLL and fast converter control. So DC link controls are really fast control, right? Not necessarily slow controls. Then RMS model wouldn't be able to capture those controls and its impact on the system. And that's where you need to go with the EMT model, because it has the capability to capture those fast dynamics associated with IBR. So again, try and link this right hand side of the figure to the left hand side of the figure. There are horses for courses, right? What you really want to study? What's your objective? If your objective is lightning phenomena switching surges, I think no RMS model can give you insight. You need to go to EMT model. Do you want to look at the impact of the PLL dynamics, right? If you got a corrupted voltage waveform, then PLL would struggle to latch on to the system, right? And it would compromise the performance of the inverter based control. Then again, you need to go to EMT model. But if you're interested in just looking at the line loading, okay, if I strip one line, what's the load on the second line, right? You probably okay to use RMS model, because that's perfectly okay if you are looking at transient stability, right? In a high synchronous machine dominated area, probably it's okay to use RMS model. So again, there are horses for courses, but this slide gives you a really good picture of what you want to study and what tool you should be using to study. Again, fit for purpose tool is important. Okay, don't use EMT for the sake of, because everyone is using EMT, so I should use EMT, or everyone is using RMS model, so I should use RMS model, right? Just make an educated guess. The slide gives you a bit of a idea about the differences between RMS and EMT model. Again, I have used the RMS and EMT, right? Because I'm trying to be tool agnostic. There are tools which works good on RMS model, and there are tools which works good on EMT model, right? Which uses EMT model. So that's I'm being agnostic of those tools, right? So RMS model, I mean, it doesn't really represent three-phase system, right? It's kind of a single phase equivalent of three-phase system, if you like, right? So if you really want to interested in the unbalanced fault and its impact on the system, then probably you need to go to EMT tool, which has a capability to capture those dynamic associated with unbalanced system. Representation of PLL, phase lock loop, if you have done the course or if you have studied the IBR, the PLL is kind of a heart of it, right? The phase lock loop. So RMS model, I mean, there are models which provides you a simplified representation of PLL dynamics, but they are again simplified representation of it, while EMT model has a capability, I use the word carefully, right? It has a capability to capture the PLL dynamics as long as it is in the model. Right? RMS model, again, it's a limited ability to model fast converter control and DC link dynamics. People know that it's really, really fast. RMS tool doesn't have that bandwidth to cover it, while it is possible to capture those dynamics using EMT model. RMS normally less suitable for IBR dominated power system studies. So if you got like 1 or 2 IBRs, you probably okay, right? Not necessarily fine, but should be okay. But if you got a grid with a lot of IBR percentage, right? So a lot of renewables in the grid, then you probably need to think about looking at going beyond RMS model and start looking at EMT model. Okay. Particularly with the grid having a high penetration of inverter-based resources. This thing comes up every now and then. Computational burden. Those who have used RMS model, they know. Okay, you click the button and within a couple of seconds you get the results out. It's straightforward. Right? You got 10 scenarios. You can assess 10 scenarios within a minute, right? And if you're good at Python, you can probably do it under a couple of seconds, right? But EMT models are slow, right? They comes with a higher computation burden. It needs a lot of computation time because the time step at which it runs often are in microsecond time frame, right? So it takes time for computing every state of IBR at every microsecond, right? Because all the PL and everything is model, assuming it is model, it will take time. So it has a computational burden if you are interested, if you are looking at the EMT models. These are some of the features which is possible using EMT, real source code model. It is possible in EMT. When I say real source code model, that means they are proprietary information. Often it is possible that a developer or a generator can provide you with the EMT model with the source code, but of course it will be black box, right? So you wouldn't be able to see their proprietary information, but you would get a really sufficient detail of it. There are critical elements such as phase lock loop, fast switching transient of power electronics can be captured in EMT models. If you got a corrupted voltage distortion, right? So those are the things which RMS model doesn't capture, like when the fault happens, right? In RMS model it just goes down and this comes up, right? But actually there are 3 phases which are corrupted during the fault, right? Even after the fault you wouldn't see a steady state immediately. All these features can be captured in EMT model, right? Again, there are horses for courses. What do you want to learn? What do you want to study? Far more realistic than RMS model, particularly in an inverter-based resources dominated grid. So you got a lot of wind, solar, and batteries. It's dominated, right? Of course, it's slower than the RMS, and building a larger model is very, very complex. It's not that straightforward and easy. One example of RMS versus EMT. So one on the right side is from the prediction of the real disturbance, and the one on the left is the simulation. So one on the left is a LCC model, LCC HVDC. You apply the disturbance in an RMS model, and you can see the voltage will come back, stays there. The link will go through FRT, come back, and then stays there. If you do similar exercise in EMT, you would see that the link has tripped. DC link has tripped because of the commutation failure and etc. And the same you can see in the voltage profile. One on the right side, it captures the converter P1 oscillation. So you can see that orange line, you can see the voltages are oscillating. While if you do the similar exercise in RMS, then it essentially fails to capture those kind of interaction. I have some examples later on as well. Okay, I'll probably use the first bullet point and then I'll skip through a few slides. So RMS model and EMT model, right? Try and avoid using this word RMS model on EMT platform. So if you convert your RMS model into EMT model, you are not necessarily going to get anything more. It's the same control system, same lead lag controller, same PI controller. You're converting that from RMS to EMT, you're not going to get anything more. If you really want to get anything more in EMT, you need to build those dynamics associated with the DC link control, inner control, outer control, and PLL. That's where the reality of EMT would come into place. So where EMT models have been used, okay? These are some of the examples from Australia, but it's pretty common across the other system operator. So it can be used in system operation to look at the converter-driven interaction, system strength area, system strength limited wise. It can be used to support the inverter-based resources. So you can develop operating envelope, and you say, okay, well, if your system has this many synchronous machine available, this much of inverter-based resources you can support. You can't support more than that. If you need to support more than that, you need to bring more system strength into the grid. It can be used for assessing complex phenomena such as torsional mode of oscillation, commutation failure, extended commutation failure, etc. Can be used for model validation and system restoration. If you are getting a new generation connection in your grid, you can use EMT to assess its performance, particularly for IBR. I mean, not necessarily for synchronous generator, but if you are getting a application from a wind farm or solar farm developer that they want to connect to your grid, then you can use the EMT model to assess its performance of the to the system. Future system dynamics and other applications, I'll probably skip through this slide. Let's quickly run through how to develop this model. Often this question comes to me that, okay, well, these models are complicated, very hard to build bigger model, larger model. It's okay to assess 1 or 2 wind farm or solar farm, but if you want to build a grid with, I don't know, 100 bus, I don't know, tens of IBRs and tens of synchronous generator, how do you build it? It's not that straightforward, right? It is actually, right? Once you do it, it's really easy to build large scale EMT model. Of course, when you're doing it first time, it's going to be difficult, right? But once you do it, it's easy. So it essentially has this 5 critical component. One is a network model, lines, buses, transformers, right? These are the network model, which you can get it from any power flow system condition, right? Any power flow solution. Then you got IBR model. Normally it is provided from the proponent. If it is not provided from the proponent, then you need to build your IBR model. Then you need to have interface between the network and IBR, which you can see it here, right? There is interface between network and IBR. So it's like a connection between IBR and the network. You need to do initialization. This is a bit of a tricky exercise, but once you do it once, it's easy. And then you need to develop a network equivalent. So these are the basic 5 steps of building a wide area EMT. It can be hundreds of buses, it can be thousands of buses. Essentially, this principle is not going to change a lot. Okay. So I briefly discussed about network models. So lines, static reactive compensation, normally available from the TSO. IBR model, normally available from proponent or transmission owners. Generally, it's preferred that it should be site-specific models. Transmission line modeling, I'll probably skip this one, but let's look at the typical IBR model, right? So when you get IBR model, these are the basic component of IBR model. You got a power pack controller, which is sitting here. You got a PV array or wind turbine, depending on whether you have a solar farm or a wind turbine. You got a PV array or wind turbine here. You got an inverter control, which controls the either wind turbine or a PV array inverter. You got a scaling component somewhere sitting here, because normally you wouldn't get like hundreds of wind turbines model, right? They are normally aggregated. So you will get one wind turbine, and then you scale it up to potentially tens of hundreds of wind turbines, depending on the size of the wind power plant. And you will have a simple grid, which is kind of a grid equivalent, right? So that's power controller, which kind of controls the output of the solar farm, and inverter controls the inverter. This is the basic layout of a typical model, a typical IBR model. You probably need to work through the interface between network model and IBR. At one point, I think I mentioned that IBR, when you get it from the generator, right? They give you that, okay, well, my IBR you need to run at a particular time step. They might tell you that, okay, well, you need to run at 1 microsecond time step, while the network time step might be different. So you need to somehow have some interface between network and IBR, right? At the end of the slide, there is one good reference. So if you read through that, it has some steps. How do you develop those interface, right? But this is one component, so I'm not going to go into detail of it. But this is a component which kind of links network and IBR, and make sure the information is passing from network to IBR and IBR to network at every time step. Then you get the initialization, right? So those of you who have used this phasor domain model, and whether Dixaland or PSSC, when you run the dynamic simulation, right, you might be seeing this initial condition suspect error sometime, right? What it does, it basically from steady state power flow, it calculates where the state should be to achieve that steady state condition. So it back calculates everything. It does the initialization. Now EMT model by itself is not going to do that for you, unfortunately. So you have to do it by yourself. So you look at the end state and decide where your initial state need to be to achieve that end state. So this is one of the method you can do it. So you need to backward calculate the states. Once you build this one, you can apply that for any other synchronous generator. Again, in the reference, it has some examples. You can follow through it. Same for IBR. Now IBR, when you get a model from IBR, right? Normally there are a bunch of codes, right? C code. It's very difficult to initialize C code, right? Because there are so many variables. What do you do, right? This is a trick to do it. What you do is, you initially, when you are doing the studies, you connect your IBR to a voltage source. So basically, you form an island. Voltage source and IBR. You start the study, entire network. At some point, you flick the switch from IBR connected to voltage source to the grid. So initially, you are forming a small island. So it runs through, stabilize the value. And at some point, you open the switch and connect IBR to the grid. It's that simple. Although it's very complicated, but it's not complicated. It's simple. That's the logic. We do it. Okay, so that's how you initialize IBR. And network equivalent. So at some point, you need to draw a boundary. How far you want to go? Do you want to build an entire country? Do you want to build an entire continent? You need to stop somewhere. And there are ways to achieve network equivalent, right? You could have a static voltage source. You could have a dynamic voltage source. You could also have a frequency dependent voltage source. So there are ways to do these things, right? But there are options available, right? And they are relatively simple to achieve this. Some of the tools come with these options. What kind of network equivalent you use, static or dynamic? Sometimes you just want to put a load. That means no dynamics of the neighboring region is considered. Guess it's basically load. I'll skip through this one. There is an option to do co-simulation as well, right? So not necessarily you have to do everything in EMT. You can have I don't know, north zone in EMT, south zone in phasor domain, and you run the entire north and south together. So you can capture the IBR phenomena in the north zone without developing north and south in EMT, if that makes sense, right? So these are the options available to run EMT simulation. You don't have to do everything in EMT if you really not convinced. You can do RMS and EMT co-simulation together. This essentially is covering the what I was mentioning. What do you do? How do you do EMT studies, right? You got a phasor domain studies where you get a load flow. you convert that into EMT, put it in EMT model, right? All this, these are the inputs. So you get IBR model, you convert it into EMT, put it in here. You need to select the study area, you need to select the fault you want to apply. These are the things which you can actually script it, right? You don't have to do it manually, you just script it. There is a lookup table that I want to study 5 contingencies. I want to study 5 system conditions. So you got 5 load flow snapshot, and there is a table which says 5 contingency. This all the information would come in here, and it just keeps on doing iteratively. So if you got a script, it just keeps on doing it. It will take first snapshot, apply 5 contingency, run the results, store it. It will take a second snapshot, apply those 5 contingencies, and rinse and repeat. And at the end, you can look at the plotting and scripting. So you can open the output file, similar to what you do in normally in PSSC, .out files. You grab it, and then you open the channel, and then look at it. Same thing you can do in EMT. So the process is largely similar. It's a little bit different the way you process the information. In some of the tools, those information are readily available to you. While in here, you probably need to develop it. Right? Once you develop it, then it's relatively easy. Okay, so now I still got 7-8 minutes, right? I'll cover a bit about power system model validation. So if you remember, just get a water. If you remember, I was talking about what is good model. This is about what is accurate model. Those two are different things. Okay, you get a good model which gives you all the functions as you wanted, right? But it may not be accurate model. It's just a good model, right? So this is about the accuracy of the model, right? And that's where the model validation would come into the play. Okay. So why you want to do the model validation? Okay. So is to make sure that model performs according to design. So what you see on your desktop computer is likely to happen in the field. That's what you want to make sure. Otherwise, you don't have apple-to-apple comparison, right? You see, okay, everything is okay, and then in reality, a fault happens, and half of your country got backed out. You need to have a confidence in the system studies and the security and reliability, because we are all going to do system studies. We provide advice to our control room, or those who are doing the in the system operation side. They provide advice to their the people who manage the system. Right? So we need to have confidence in that advice. It helps to create to do proactive assessment of the new risk. Right? So if you see a new, like you got a really good model, you have a very good confidence they are accurate, and you started doing some studies, and then you find something new phenomena which you haven't seen it. But if your models are accurate enough, it gives you a confidence that the new phenomena which I'm seeing it is going to be right. It's not just a fluke, it's not a modeling artifact, but it can happen. I have some examples. If I get a time, I can come through that example, which is totally new phenomena we observed in the simulation. And that there was a question, okay, well, that's just a simulation. What's the confidence? Is it really going to happen? And we ended up doing a real-time test. Like there is example for that. Real-time test to apply same disturbance which was observed in the simulation, and look at, is it really going to happen? And it did. Actually, the similar phenomena which was new was appearing in the model was actually surfaced in the real-time test in the grid. So it gives you confidence that, okay, I know my IBR model is really accurate because it came from OEM, it got all the source code model in there, source code information in there, right? Network model is reasonably okay because it's a transmission line, right? And SVCs and other things. If you got this confidence, then you see new phenomena, you can say, yes, it can happen. So greater confidence, I mentioned about the power system studies. So This slide tells you where you can do model validation, right? So those OEMs, those who are in OEMs and going to work in OEM, they can do a certification testing in their site, hardware and loop testing facility, which OEM or developer can do it. There are post-commissioning model validation, which TSO, DSO, and others can do it. There's a stage testing, where essentially TSO or system operator can do it, and system disturbance validation. So if the event happen in the grid, what you do is you capture the data and you feed this data into the model and see how the model is responding. Is it responding to similar to the reality or something different? So that's called system disturbance validation. There are various approaches to do system validation, right? So this is a simple approach, a playback, right? What you do is you capture the data from the grid and feed back the voltage and frequency to the model, observe the active and reactive power of the model, and compare it against the reality. That's a very simple way to do the model validation. It's kind of a SMIP kind of exercise, or often call it a playback approach, right? But you need to wait for the system disturbance to occur, right? Otherwise you can't get the data, and you can't get the data, then you can't validate the model. So you are kind of relying on the natural disturbance of the system. Once the disturbance happens, you can proactively get the data. And it validates the model on one operating condition only, because that disturbance happened when as an example, solar farm was generating 50% of its maximum capacity. So you can validate solar farm at that one particular operating point using that disturbance data. Right? So that's another drawback of that. But at least it gives you confidence. These are some of the examples that how it looks like, playback approach. So this was one of the solar farm response. You can see in reality after the disturbance is kind of ramped down for whatever reason, and it kind of landed here 22 megawatt from 50 megawatt. That's the real disturbance. When they did a playback, what they did is they took the real samples from the field, injected those samples into the model, and the model says I'm going to do like this, which is totally different than what happened in the reality. So it gives you confidence that, okay, well, this model, something need to look at it, right? The model which we have is not necessarily behaving how it's going to happen in the grid. Okay? So that's kind of a not so good example. On right side is a good example. You can see what actually happened on the field and what actually the model is telling you. It's a good model, right? Because this was happened on the field when I used the data using playback, injected into the grid. It gave me a kind of similar response. So that means the model is good for that operating point, at least gives me a confidence. This was for I think it's wind farm. Yes, wind farm. Yeah, you can see it. And this is one of the response from synchronous generator, right? These are EMT response, these are RMS responses. But at least this gives you confidence. There is a dotted line is a kind of a 10% error bound, right? No model is going to be 100% accurate, right? You need to have some kind of a relaxation. Right. But you can see it gives a good confidence that the model is going to reflect the reality. Of course, there are small variation here and there, but that's okay because you can't model everything. There are other approaches like a wide area integration approach or stage testing approach. So, wide area integrator approach is you take the data from various locations for disturbance, build the network, apply the disturbance as it happened on that day, and validate the entire wide area. So like initially what we did in this previous example was one plant and one data. Here you have multiple plants and multiple data, but you actually replicate the fault or disturbance on the simulation, which is a little bit complicated because you need to make sure that when was the fault. Is it like a 10 kilometer from the line, 20 kilometer from the line? Was it a line to ground fault? Does it involve any impedance or not? You need to do a little bit of tweaking, but you can do that, right? And then that gives you, it's highly complex, I mentioned, requires significant effort, requires high resolution data at several points, but you can validate the entire region. It's a collective response. And the stage testing is when you apply the disturbance intentionally on the grid. You go on the field, apply the disturbance, capture the data, and validate the model. Okay. Not straightforward, little bit challenging to do it, but it can be done, right? Like it's a highly complex, it requires rigorous examination of system because you are actually going to apply disturbance on the field. And people often don't like that for all the good reasons, right? We really don't want to do that. Some of the examples of wide area integration. So one on the right side is from the System Black event happened in Australia in 2016, where you can see the dotted lines are HSM. HSM is high speed monitoring devices, so it's like high resolution field data. Dotted line, and then grayish line is RMS model, and then this kind of dark line is the EMT model. And this is called the wide area integration approach. So this was like entire region model in EMT, model in RMS, apply the disturbance as it happened on the field, and then see how it is responding. So you are actually, in fact, validating the entire region, not one plant, but every plant, but only for that disturbance, right? One on the left hand side is a converter interaction. You can see that the EMT model, what it picked up, and what was the reality on the field. Okay. This is again an example of wide area. Intentional testing, I was mentioning, stage testing we call it, where you actually apply the disturbance on the field. This was from the real example, right? There is a reference to it, I think, towards the end of the slide. I encourage you to look at the reference, where you actually apply the fault on the grid, measure the data, and then look at how the model is going to perform for that same kind of a fault. Okay. And you can see it's reasonably okay. I'm not saying it's super accurate, but at least it captures the key characteristic of ride through, right? So you got a fault, make out drop top, and after some time make out comes back, and you can see a little bit of a change in oscillation, but this is like entire grid, right? So you got a lot of unknown parts as well, but at least it gives you confidence that okay, after the fault it comes back in this time, reality the model comes back in reasonably same time. Okay, so in summary, I think we are right on time, so it's 1 hour and 5 minutes, good. Again, remember, essentially all models are wrong, some are useful. Okay. So I discussed the need of the power system model. Fit for purpose model is important. Right? Don't just do system modeling for the sake of modeling. Make sure what you really want to study, and find the model which can help you to understand that phenomena. We did discuss about the characteristics of RMS and EMT models, right? So where to use, which model to use, what are the intricacy of EMT and RMS models, differences, similarities, challenges, opportunities. We all discussed that. I quickly brushed through the developing wide area EMT models. So I went through those steps, like very, very high level. And the general principles of model validation. So if you want to validate the model, what are the general principles? So these are the things briefly covered, right? So summary of it. These are some of the good references. So I encourage you to go and have a look at those references. Right? A lot of good information in there. Some of the secret brochures, some of the IEEE publications. Slides would be available to you, so you can have a look at it. And that's end of the discussion, right? So, sorry? I can, if there is a time. We take a question and answer, and then we do the Westmore one. Yeah, that's fine. You got any questions? I got another presentation which I did a while back, last year in general meeting, which I think Gan was asking if you can redo it that again. It might be interesting for the audience. I can do it, but before that, I'm happy to take questions. Sure.
I hope you can hear me. I mean, we as a student, we don't have access to the data, or we cannot create the disturbance in the real-time system, right? So rather we rely upon the available resources. You were like mostly talking about the backstage working of those simulators available for us. Am I correct in understanding that?
Well, I think what I was pointing towards is general principles of it, right? I understand, I completely understand your question that being a student you would have a limited access, right? But the philosophy doesn't change, right? When you say limited access, that means you might not have real-time data, right? But at least if you understand the basic concept of what you do, how to do it, then once you get real-time data, it's just a matter of applying it, right? So same principle as example, like if you want to develop a large-scale EMT model, right? As example, you can, in the absence of site-specific model, you could just assume this model you have is a site-specific model, okay, different time step, and then this is the network model which is on different time step, and you make it work. Same principle you can apply when you go to industry, right? So there might be some limitation being a student and not having access to those real information, but that shouldn't stop you to practice these principles, right? These are the basic principles, you practice it, and once you practice it, once you got access, you can easily apply it. Does it make sense? Does it answer your question?
Sorry, last one.
Yeah, sure.
Which platform do you use for this modeling? Like there is a different platform, like MATLAB. You can have some blocks of something. MATLAB is a one example of.
Yeah.
But now Python libraries are coming like Panda, Power, Pipesite, etc.
Yeah. So for most of the system operator, RMS modeling, they do it in PSSE. Most of the system operator, not all. For EMT modeling, lot of system operator use PSCAD. There are quite a few system operator who use EMTP, and there are other tools out there as well, right? E-tron and other things out there. So those are the tools which a system operator would use depending on the availability, right? Because we are working with a kind of a generator model. So if we are getting a model which is really good in one particular tool, proprietary tool, then we have to use similar tool, right? Because otherwise that model is not going to work with other tool. So there are some limitations around it, but most of the things like PSSE, we use PSSE, PSCAD, EMTP. There are other tools out there as well which we can use. I think the intention is the core principle of using it, not necessarily the tool. And that's why in my discussion I was always talking about RMS versus EMT, not one tool against other tool. It's a concept I was trying to convey. Yeah, sure, there is a question in the back.
This is a offbeat question. So, few years back, around 2017 or 2018, the Western grid had PV output more than the demand. The total supply was more than the demand. So the Western grid in Australia, I am talking about, so they throttle the PV output. So my question is, do we still doing the same thing to throttle the PV output during the peak hours of the PV? We have found some solution to use that PV output. And my second question is it possible to analyze power flow considering PV at all buses? PV, like photovoltaic at all buses of the power system. Is it feasible or is it logical to do this thing in power flow?
So, good question. I guess you are talking about the distributed PV or transmission connected?
Transmission level.
Transmission connected PV.
Yeah, inverter-based resources basically. Yeah.
Right.
PV specifically.
Basically PV. Yeah. So, okay, on that incident, I'm not across the incident, right? So I'm just going to make some guesses. The constraint, curtailing the IBR, right? You mentioned example of PV and large scale. To me, they are same, large scale PV or large scale wind farm or batteries, right? You curtail them when there are system security issues, right? So I'm guessing you would have enough supply demand balance to meet it. But if you do not have a sufficient, let's call it system strength to manage those PV online, then you have to curtail back. Because the curtailing had a lot of reason they curtail it, right? It could be because there are 3 lines going out, okay, in day-to-day operation. You can run the PV plant at full output because you've got 3 lines to export that power. If you lose 1 line, you still have another 2 lines to carry that power. Now, if you are taking 1 line on the maintenance, you are relying on 2 lines to export that much of megawatt from that solar PV as an example, right? If you trip 1 line, you might not have enough capacity to get that line to carry that much of PV. In that case, you need to curtail it, right? So there could be a lot of reasons why there was a curtailment of IBR. I'm not necessarily going to pick on PV, right? Because you mentioned about the transmission connected PV, not the distribution connected PV, right? So that could be a reason why it was curtailed, right?
So it was mentioned in the report that supply was more than the demand. No constant was mentioned in the report. That's why I asked. Did we find any solution for that? How to maximize the PV output? We are still doing the curtailment of the PV output. That's why I asked.
Okay. No, look, if we supply more supply than the demand, there are a number of reasons it can be done, right? One, first we need to make sure you have essential system security services on the grid, right? So you need to have a sufficient fault level, sufficient voltage control, sufficient frequency control, sufficient inertia in the grid. Right? Now, when you have a lot of supply available to you and you got access PV generation, there are options. You can curtail synchronous machines, right? But when you curtail those synchronous machine example, you are going to compromise on the inertia. You would compromise on the fault level, right? Which not necessarily you are going to get it from PV as an example, right? So your option available is to curtail PV rather than curtailing a plant,
that
right?
was the gist option.
Now, in terms of how to manage those things, there are other options available. Like if you are looking for frequency control, you can get those from batteries. They are really good in frequency control. If you are looking for inertia, which was probably the reason as example to curtail the wind farm, you can go and look for the synchronous condenser, which provides the inertia, but not necessarily you need megawatt from there. Right? So that megawatt can be available to solar generation when you replace synchronous generator with synchronous condenser, if that makes sense, right? So those are the options can be considered when you really don't want to curtail IBR or distributed PV. But it takes time to develop those solutions in the grid. It's not going to come overnight, right? It takes time to build new asset. It takes time to build those technology and have a confidence in those technology to operate. Does it answer your question?
Yeah.
Okay. What was your second question? I think you mentioned.
I just asked, is it logical to inject IBR PV at each bus at transmission level?
Is it to inject or consider in study?
Consider.
I don't see a reason not to consider it. Right?
Okay.
Yeah, you could have a power flow which is essentially passive, right?
Yeah.
Your most of the generation is coming from the distributed PV and transmission connected PV.
Yes.
Yes, you can consider it. There could be consequences of not having system services on the grid, but definitely you can consider it.
Okay.
Don't see a reason not to consider it.
Thank you.
Sure.
Hi, so thank you for the presentation. I'm Jet Chen from Siemens Energy. Just a question on because at the moment now, the trend, at least in Malaysia, for the connection process, it's not compulsory to provide an EMT model. So do you think that this will be a challenge in the future when somehow the TMB would really need to implement or consider wide-scale EMT model?
I think so. Because it might be required to get those models at some point in time. So if we don't have a model of the existing plant in 10 years down the line or 15 years down the line, someone need to develop those models or go back to proponent to ask them. And it may happen. This is a dynamic industry that proponent has exited the market. So where do you go and ask for the model? New proponent say, well, I'm new proponent. I don't have information available to me. Right, so it's better to get those models, maybe use it or not use it, that's the secondary thing, right? But get those models available while the plant is getting connected. So you don't need to have those retrospective correction to do. Because there are utilities across the world where they don't have a model for legacy plant. That's what they use, legacy plant. What they do, they need to build it by themselves, right? They need to put an effort to build those models. But now is the opportunity. If the plant is getting connected, there is awareness about those models. Most of the OEMs, including Siemens and others, they have those kind of model available to them, right? It's not that they have to build from the scratch. But some of the utilities, they don't ask for this model because it's not in a grid code, as an example, right? But yeah, of course, it is not in a grid code, so it's not obligation to provide it, right? But if it is available, if it can be provided to utility, it can be used in the future, right? So you don't need to go back and redo it, right? So that's my take on your question.
Just another follow-up question. You mentioned in one of your slides that it is possible to convert the existing RMS model to EMT. What are your thoughts on it? Is it really straightforward method, or because if it's black box, from my point of view, it doesn't seem to be possible, right? To convert a black box RMS model to EMT.
You are right. So if it is a black box, it's practically impossible to convert. That's the reason why you have the black box model, right? But if you got open source model, as an example, synchronous generator model, right? They're basic model, right? It doesn't get too complex. So if you got open box synchronous machine model, you can convert that into EMT model, right? It's not necessarily going to give you any more information than what RMS model can give you, because essentially you are converting the same algorithm from RMS to EMT. But it can be used to build the entire wider area network, because in the wider area network you need all model in EMT. So you can convert those open box model into EMT, but the black box is I think is very difficult, if not impossible.
Thank you.
Sure, I have two questions.
Hi, here. Thank you for the presentation so far. So my question is, at what point do you have to start integrating, EMT studies into system planning in terms of like what percentage of renewable penetration? Because from a financial and like time perspective, you have to invest effort into it, but then you need to justify the findings, right?
It's a very good question. I don't think I have answered at what percentage of renewable penetration you need to start looking at EMT model, but I got two examples which will help you. I think one happened in Northern Hemisphere where there was only one wind farm which was interacting with the grid. So when you look at the percentage of that one wind farm generation to the entire country is practically very low. Right? But those issues can be picked up by EMT, not necessarily by RMS. So that's one example, right? One extreme. The second extreme is from other country where there were few solar farms were interacting with each other, right? So you have a bit of a percentage of RE available where you need a EMT model to look at it. So again, it's horses for courses, right? If you go to IBR, maybe check it with EMT model. Not necessarily you have to develop the entire grid in EMT, but you can get those EMT model from IBR. Do a kind of a SMIB analysis, if that makes sense, right? So single machine infinite bus kind of a system, and then check how it's going to perform under different short circuit ratio or short circuit strength, and that's where you can start looking into it. As you have a more concentration of IBR, that's where you need to seriously start thinking about EMT modeling, or at least a modeling which can capture those phenomena. Okay. If you got a system which is very high synchronous terminator system, your SCR levels are really, really high, unlikely that good manufacturer plant would give you an issue. But as soon as you start looking at close proximity of IBR, so one wind farm, next door another wind farm, and then you got solar farm coming in, there are few batteries coming in, that's where you start looking at EMT modeling. So it's kind of a bit of an educated guess you need to make. So there is no rule of thumb that, okay, this percentage is something where you start looking into EMT. Okay. Like HVDC system, right? People look at EMT modeling to understand HVDC system phenomena. It's just a HVDC system connecting two regions. There is no percentage of renewable there. But they start looking into EMT, just looking at the HVDC system.
And in the context of like AEMO's ISP, integrated system planning, for example, do you look at EMT studies when you decide on capacity expansion, or is this more on when you actually implement the individual projects that you need to go into these studies?
So I understand the AEMO planning studies do the economic modeling. So ISP and other documents are more of a cost benefit analysis and economic forecast, what needs to be built to achieve the target, right? So it doesn't necessarily feed into, or there are no EMT studies or analysis goes into those kind of analysis. These are more cost benefit economic analysis of in ISP. Okay, can probably stop. Yeah. Oh yeah. Okay. Okay. All right.
Thank you, Dr. Nilesh. So I just have a question. So I'm just curious, in countries like Australia, so for those states regarding the power utility or the government agent, if you do the R&D or some system level simulation, so which kind of models they use more often, like the RMS or the MT, or if particular, could you mention the name of the software for the Australia, like utility?
So Australian utility, we use a mix of both models, RMS and EMT, because there are some studies which looks at the classical transient stability or dynamic voltage collapse and thermal overload contingency analysis. So we use a phasor domain transient model, which is RMS model, and looking at the converter interaction, developing system state limited device, we look at the EMT model.
Okay, there's one question from online participants. Allow me to read the questions. How critical is IBR modeling in power systems based on your experience? And can we determine optimal penetration level to the grid from our modeling? I think that's a similar question to the gentleman.
Right. Yeah. I think it's very important to look at this this EMT modeling, right? Particularly if you have IBR. I mean, there are a lot of examples I quoted, right? Impact of IBR and what tool can capture what or what models can capture and what type of models can't capture. So I think it's pretty standard to consider EMT modeling in your day-to-day practice. At least you start learning into it. At least at some point in time you start practicing it. At what point you have to draw a line? I think that's still debatable. As early as possible, at least start looking into those kind of a model and the phenomena. I think it's better.
Okay, we better take the last one.
Hello sir, thank you for the presentation. My question is that there is two models you mentioned, RMS and EMTP. So both the models are depend on the what we call the issue we are treating, because the type of the model, just like a real time, we can consider the EMT is more suitable for that. For RMS, if not a real time, just like a planning thing or something, we can consider for that RMS model. So which issue is more prominent in, if you consider the inverter based resources, so which issue is more come in the system? So for that we consider that model according to the issue, no? Yeah. If 70% or 80% the more prominent issue is coming, which one is that one?
So that's on the left hand side of the box of this stability phenomena, right? This one. These are the one which are largely driven by inverter based resources, right? And to capture most of this oscillation or most of these issues, I should say, people rely on EMT models. Alright, so if you got a system which is highly dominated by synchronous generator, then probably RMS modeling is for you, okay? But as you move towards synchronous dominated grid to IBR dominated grid, you need to start thinking about EMT modeling. And at least I don't know where is the draw line, what should be the percentage. I think that's probably a question for intelligent engineers like you. Come up with an answer. This is the percentage where we want to draw a line, that below which we should be okay with EMT model, RMS modeling, and then above that should look at EMT modeling. But to answer your question, the phenomena associated with this is largely driven by inverter-based resources. Okay. All right. Got a question or one more? Or?
Okay. Yeah, we have 4 minutes left.
Yeah.
So basically from your experience on EMT and also the rest related to IBR, I think we have seen the Australian market is quite liberalization from 7 states, 5 states, there's a trading. But when it went to Malaysia, I think we have seen that we have a lot of synchronization. I think the government have been targeting 45% or even 70% of the renewable. So it's part and parcel of the intermittent. So yeah, I agree with you. Just now you mentioned about there is no real value in terms of at which juncture. But again, if let's say there's available software such as Plexos, if you want to integrate with the PSSC or even ETAP, is it can also be considered also, because I think on shelf there's a lot of software outside there, but when it comes to you want to measure the energy transition, when it comes to the, we call it the RE penetration based on the EMT model, what will be your take on this?
Sorry, I lost the question. So your question is
Okay,
about?
my question is that there's a Plexos software that you can use also to integrate with the PSSE or even with the ETAP, or to calculate some of the we call it energy transition. We call it the progress.
Plexos model here.
Yeah, Plexos. But the Plexos, such as Plexos, is it based on EMT or IBR or what?
Plexos model.
Yeah, Plexos.
Plexos, I understand, is a cost-benefit analysis model, right? This is tool used for the planning studies,
Okay.
where you have a economic input, short-term marginal cost, long-run marginal cost of the plant. You have a forecast of the wind and solar, and you have a forecast of the load, and you try and match those demand with the supply available at the least cost. So what is the least cost way to achieve that demand? I don't think the Plexos does any power system modeling. There would be some
Integration.
modeling in there. As an example, sometimes you have a constraint on the line, so if flow doesn't go above that constraint. But I don't think that looks at a detailed power system modeling. It's more of an economic expansion of the grid.
If it's related to the energy storage related to EMT or IBR, is it, how is it?
I don't think EMT or IBR is considered in a Plexos, right? It gives you a kind of economic outlook, and someone need to convert those economic outcome into appropriate modeling. So if economic outcome is saying that you are likely to have 80% of renewable on 1st of January, 12 p.m. as example, right? Then someone need to convert that snapshot of economic expansion into power system tool, and then run the studies to understand what issue is likely to happen, right? And that's where, if it is a high IBR scenario forecast, you probably need to look at the EMT. But there is a question about forward-looking EMT models as well, like 1st of January 2030, what model you should use it, right? It's the future. So it gets a little bit uncertain. All right, stop here.
Okay, I think we'll stop here. And thank you very much once again to Dr. Nilesh Modi for his presentation. So before we end, we would like to invite Dr. Mizana, the chair of IEEE Power Energy Society Malaysia, to give a token of appreciation to Dr. Nilesh Modi.
Thank you. Thank you very much. The green one. Thank you. Thank you very much.
Okay, thank you very much. Okay, for the attendance, I mean, we will prepare a QR code. Anyone that would like the attendance to be recorded, please scan the code, and then we will record the attendance for you. Okay. 2 minutes, please.
Oh, yes, please. Yeah, that's oh, thank you.
Okay, in the meantime, we will take a good photo. Please remain seated. I will take the photo from here.
Okay. I am okay.
Huh? Okay. Diambil yang kamera tu. Yeah, we have refreshment outside. Please help yourself.